Hello, my name is Alexander Grishin, and today I would like to tell you about our recent paper, Controlling Overestimation Bias with Truncated Mixture of Continuous Distributional Quantile Critics. This paper is written by me and my exceptional colleagues, Arseniy Kuznetsov, Pavel Shvechikov, and Dmitry Vetrov. One of the main problems of reinforcement learning is overestimation bias. It arises when agent tries to approximate its own future returns and then maximize this approximation over actions. Since this approximation is always imperfect, this maximization inevitably leads to overestimation of agent overestimates its own performance. And this overestimation, this error, propagates through time, through temporal difference learning, and it degrades severely the performance. Motivated by this problem, we propose a novel method, Truncated Quantile Critics, or TQC. TQC combines three main elements. The first one is distributional critics. Instead of single value, our critics output the whole distribution. Our critics try to approximate the whole distribution of returns. Second element is the ensembling of critics, which promotes the stability. And last, but the main, in fact, actually the main part is truncating the mixture of distribution. We truncate the right tail of the mixture to alleviate the overestimation bias. This structure, these elements, leads to several new and interesting properties of our method. The first one is that we incorporate stochasticity of returns into the process of overestimation control. It is important because this exact stochasticity of returns is the root of the overestimation bias, is the root of the problem. And our method is the first which uses this root to control the overestimation. The second property is that our method provides fine-grained level of control. By varying hyperparameters, we can choose the exact level of overestimation control that we need. The third property is that we decouple the overestimation control, the process of overestimation control, and the process of ensembling. So we can independently vary the level of overestimation compensation and the number of critics. We benchmarked our method TQC on the Majoko locomotion suite and compared our method to the previous state of the art, namely soft actor critic, orange, twin delay DDPG, green, and truly proximal policy optimization, blue. Our method outperforms them all by a significant margin, from 20 to 30%. Now I want to show you how does this performance increase looks like in practice, in environment. So we compared soft actor critic, SAG, previous state of the art, and orange, and our method TQC, red. So the goal here is to run as fast as possible, and under some fixed amount of interaction of data. And now it is clear that 20 to 30% increase in performance translate to almost twice as fast agents. Now let's dig into more details of our method. Let's start with some notations. We have the usual interplay between the agent and environment, which is described by states, actions, and rewards. One of the main goals of agent is to find the state action value function, which is the averaged future return. And agent tries to approximate it with some parametric approximation q theta. And here the problem arises. Let's imagine there is some true q-value function blue line, but we have access only to some noisy samples blue crosses. Then we try to fit our approximation to these blue crosses. We do it, of course, we do it imperfectly because we have some insufficient amount of data. We have some noise, and it ends up with some distortion that our approximation is not perfect. And then when we try to maximize our approximation, we come up with some overestimation. We often come up with some overestimation with some error. And here is a visual intuition. And then I want to describe it from more formal standpoint of view. Essentially, what we have is the maximum over the approximation. Let's average it over this zero mean distortion. Using the concavity of the maximum operator, we can apply the Jensen inequality, and the averaged distortion vanishes, and we end up with the maximum over the true q-value function. And now it is clear that the predicted maximum is always greater than the true value. In practice, we don't have the maximum, but we have the policy which tries to maximize our approximated value function, and the policy exploits any spontaneous, any erroneous overestimations, and during the temporal difference learning, this overestimation is propagated through time, and even some positive feedback loop may occur. So how do we handle this? Let's start with the existing methods, namely soft critic. Let's focus on the soft policy evaluation, on the training of the critics. So we sample some transition from replay buffer and then plug it in the Bellman equation, regularized with the entropy term. Then this target function is used as the regressor. We try to fit approximated q-function to this target. In TD3, in the second method, they offer some mechanisms to avoid the overestimation. They introduce two q-value functions, two independent q-value functions, and then instead of one q-function, they use the minima of these two independent q-functions. Intuition behind this is as follows: if some of these two functions spontaneously overestimate, we do not expect the same will happen with the second q-function. It usually will smooth down this overestimation via the minimum operator. This approach has several limitations. The first one is that this bias control is coarse. It means that, for example, using the two q-functions under the minimum operator could be not enough to compensate the overestimation, but using the three q-functions under the minimum could be too much already. So, and the second problem is that in some sense, this aggregation, this minimum operator is wasteful because we throw out we use only one prediction throughout the other prediction. To overcome these limitations, we offer the solution TQC. So in TQC, we have the following steps. First of all, we have some S prime and A prime next state and next action from the apply buffer. Then we feed this state and action to our distributional critics and end up with n critics times m atoms predicted by critics. Then we pull all these atoms together, forming some mixture of n times m atoms. Then, to alleviate overestimation bias, we remove topmost d times n atoms, or d per critic atom, and end up with some with the truncated mixture, which has lower expected value. After that, we apply the usual discounting and shifting by the reward and the entropy of the policy. These steps leads to the computation of target distribution. Then we use this target distribution as a regressor to each of the critic networks. We apply quantile regression loss, which is exactly the loss which is used by original quark dequaint paper. In fact, it just moves atoms of each of the network to the positions of the quantiles of target distribution. And after training of each of the critic networks, we train policy as optimize it by maximizing the non-truncated average of all atoms of the mixture. Now let's return to the contributions. Again, the first contribution was using the return stochasticity for overestimation control. What does it mean? Let's imagine that we have two return distributions. The bottom one with the smaller variance and the top one with the higher variance, but they have the same mean. So higher top distribution has larger variance, and we expect it to introduce higher overestimation bias. Now let's apply the truncation to both distributions. Truncation effectively shifts the mean of each distribution. And now we can see that this shift directly corresponds to the overestimation compensation. And now we can see that with the increase in expected overestimation bias, our method increases the level of compensation. So truncation perfectly accounts for the overestimation bias. And this connection between the variance of the return distribution and the overestimation bias we see at the exciting new avenue for research. The second contribution is that our TQC provides fine-grained bias control. Let's look at different hyperparameters. X-axis is the fraction of dropped quantiles. So with the increase of fraction, the overestimation compensation increases. And while moving along the y-axis, the total number of quantiles per network, the resolution of the compensation increases. So effectively, we can move left to the right to increase, to strengthen the compensation, and the discretization of this process depends on the y-axis, on the resolution. The third contribution is that our method decouples overestimation control and the ensembling process. So now x-axis is the fraction of dropped quantiles, and in which corresponds to the process of overestimation control. And y-axis is the number of networks in ensemble corresponding to the process of ensembling. And here you can see that we can independently vary the number of networks and the degree of overestimation control. We can vary them independently. And last but not least, that our method established a new state of the art on the Manchaco locomotion suite. We were motivated by the overestimation bias, but does our method really fights this overestimation bias? Maybe we still overestimate, or maybe we already underestimate. So we conducted the following experiment. We estimated the distribution of the difference between the approximated function and the Monte Carlo estimate of true function. The x-axis corresponds to the number of dropped quantiles. So x-axis corresponds to the level of overestimation compensation, and y-axis represents the distributions of these deltas, distributions of these errors. And we can see that TQC, with the increase of number of dropped quantiles, the distribution and the averaged value, averaged overestimation, decreases. Then let's add the returns to this axis, and now we can claim that at the point where the overestimation vanishes, at the point when the average value is 0, our method achieves the highest, the highest return. Let's add the soft actor critic to this plot. So now in soft actor critic, a number of critics under the minimum operator controls the level of overestimation, and we can see the significant difference between n equals to 1 and n equals 2. Seems like n equals 2 is already too severe overestimation compensation. So let's add some, in some sense, intermediate methods. There is the version of SAC with linear combination of minimum and maximum of functions. And it can be seen as the intermediate values between n equals 1 and n equals 2. And then add the returns to this plot for the versions of SAC 2. Now we can see that indeed soft actor critic can compensate, can compensate for the overestimation bias, but for some reason it achieves the lower return. So the sources of TQC performance lies not only in the overestimation compensation, but also it seems like from the procedure of overestimation correction, from the distributional critics, or maybe that our method can benefit from larger networks while the SAC can't. So this remains, it remains as an open question. Here is, if you want some additional details, here are some useful links. Thank you for your attention. Bye.